How would you put a telescope in a circle that is greater than the rocket that is going to send off? Is that even conceivable? Envisioning that everything is simple that exists in space or possibly in our planetary group is now there to the extent that we know it. All in space is very old, so the possibility of something fresh out of the plastic new showing up there appears to be profoundly far-fetched. Anyway, the inverse is valid. The James Webb Space Telescope, by taking unbelievably exact photos of the universe, has caused a serious overall stir. The magnificence of science is that it invites new data as opposed to dismissing it. Notwithstanding the warm gathering to new data, some of what the telescope is seeing is as yet confounding and astounding. What have researchers noticed from the James Webb Space Telescope that has them perplexed? What secrets about the dawn of history, as far as we might be concerned, has the telescope opened up to this point? How about we find out? As of late, NASA, the European Space Organization, and the Canadian Space Office collaborated to give cosmologists around the world an exceptional gift. An opportunity to brief look into the past at the making of the universe and the edge of time itself. The James Webb Telescope, hailed as the head observatory of the following 10 years, remains as one of the best logical accomplishments within recent memory. It opened this powerful window into creation not as a philosophical hypothesis, magical time machine, or imaginative illustration, yet as a substantial instrument. On December 25, 2021, this gigantic infrared telescope, more generally known as Webb, was sent off into space, determined to capture pictures of the unknown and disentangle the secrets of our hidden universe. The state-of-the-art infrared detection hardware furnished on Webb enhances the remarkable viewpoint of the universe that Hubble has given mankind. From its vantage point in low Earth orbit, Hubble has captured various never-seen pictures of far-off regions and historical periods of our universe, investigating the history and advancement of worlds, stars, and clouds. It has depicted the qualities of dark openings, exoplanets, and the sped-up development of our universe. This weighty work acquired the Nobel Physics Prize in 2011. Webb represents the next step in our collective experience of finding the universe's secrets and looking for life beyond Earth. Hubble's pictures have defined current cosmology, opening our eyes to what lies beyond and sparking our existential interest. As NASA puts it, we want to see farther and deeper. Webb can peer back to the dawn of history, while Hubble can go as far as 500 million years after the Big Bang. How is this possible? The latest space telescope boasts several advantages over early emissions. Its size is the first outstanding feature. JWST has a 6.5 m mirror comprised of 18 gold-plated hexagonal parts. This behemoth can capture light from objects multiple times faster than the 2.4 m length of the Hubble Space Telescope since it can gather more light. However, the genuine game-changer is JWST's responsiveness to infrared light. The Space Telescope can detect frequencies between 0.6 to 28.5 micrometers, spanning the mid-infrared to the red end of the visible spectrum. While most of Hubble's responsiveness shines on visible light, its optics are tailored to capture radiation from 0.09 micrometers in the ultraviolet to 2.5 micrometers in the near-infrared. Stargazers can observe galaxies that formed less than a billion years after the Big Bang by utilizing the infrared range. These far-off objects emit visible and ultraviolet light. However, due to the expansion of the universe, this radiation is now emitted at longer infrared frequencies. The best way to observe these young galaxies near Earth is through infrared perception. This, moreover, applies to newly formed stars. Baby suns are encircled by dust, which disperses visible light, darkening our view yet allowing infrared energy to pass through. Infrared radiation is imperceptible to humans. The colors of pictures captured by JWST differ from what the natural eye would see. To reproduce how the eyes see, researchers often map longer infrared frequencies to the red end of the visible spectrum and shorter frequencies towards the blue. However, this example is occasionally changed to highlight specific details more effectively. JWST serves as an all-purpose observatory. In addition to its emphasis on distant galaxies and star formation, its solid infrared capabilities enable it to recognize features in nearby planetary system objects that standard telescopes can't observe. Studying cloud belts on gas and ice giant planets, checking cloud movements on Titan, examining Pluto's atmosphere, and testing many smaller asteroids and transneptunian objects throughout the outer solar system are just a few of its initial accomplishments. When NASA's Double Asteroid Redirection Test, DART, slammed into the asteroid Dimorphos, JWST even captured a brief look at the event. This allowed NASA to study the object's capacity to alter the course of potentially hazardous asteroids that could cross Earth's path. Despite the efforts of planetary researchers to uncover the bunch of privileged insights in our planetary group, over 5,000 known exoplanets in our universe remain obscure. Most of this extra data lies beyond the capabilities of Earth-based telescopes, including Hubble. However, JWST has already begun to change this situation. While not explicitly intended for exoplanet discovery, JWST detected one around the red small star LHS 4175, 41 light-years from Earth. This planet's breadth is just 1% smaller than Earth's, but it orbits its sun in only 2 days and boasts a temperature a few hundred degrees hotter than Earth. JWST's most noteworthy strength lies in its ability to study exoplanet atmospheres. By observing transits with its powerful spectrographs, stargazers can investigate the chemical composition of these worlds. Most of the compounds important to exoplanet researchers are found in the infrared area of the spectrum. JWST's excellent resolution has allowed for the discovery of various compounds on exoplanets, including water, sulfur dioxide, carbon monoxide, sodium, potassium, and carbon dioxide. The gas and dust heavenly hatcheries known as clouds are where planets and their host stars develop. Despite their beauty, these clouds hide the fundamental processes happening inside them from an external perspective. JWST's infrared vision has begun to reveal these hidden environments. For instance, the Eagle Nebula, famous for its Pillars of Creation photo taken by Hubble in 1995, was one of JWST's starting focuses. While Hubble mostly observed obscure dust and cold gas, JWST discovered several stars that had already emerged from their natal casings. These young stars, apparent outside the shadowy pillars, are recognizable by their diffraction spikes in images captured by reflecting telescopes like JWST. These revelations offer valuable insights into the formation and development of stellar bodies. Shedding light on more mature stars, JWST has also found much more recently formed objects called protostars. These protostars are still in the process of absorbing gas and dust from their surroundings. Periodically, they release material jets that strike their dense atmosphere, causing them to emit intense red glows. The two lower pillars are among the best examples of this phenomenon. These protostars are estimated to be a few hundred years old, according to space experts. Star formation happens throughout the universe, and JWST researchers are eager to examine its various manifestations beyond our galaxy. Within our local group, two significant areas are the Large and Small Magellanic Clouds, the two largest satellite galaxies of the Milky Way. It is essential to understand these galaxies because they contain about half the total amount of metals produced by massive stars as the Milky Way. This situation resembles conditions that prevailed when the universe was only 2 or 3 billion years old and galaxies were producing stars at a maximum rate. The galaxies formed during this cosmic noon, including those we see now, were shaped by the bursts during this period. The Tarantula Nebula, located in the Large Magellanic Cloud, is the closest object in the Magellanic Clouds to mirroring these chaotic times. The Tarantula Nebula, the most prominent star-forming zone in the immediate universe, creates stars at a furious rate. Roughly 820,000 stars have been catalogued by stargazers to date, and the massive stores of high hydrogen and helium the cloud holds should be adequate for many thousands more. The brilliant star cluster R136, near the center of the cloud, contains numerous stars weighing at least 100 solar masses. JWST's initial observations have revealed unique details of the Tarantula Nebula. In the central part of the nebula, a sizable bubble has been cleared out by the intense radiation and stellar winds of the massive stars in R136. Only the densest adjoining regions, which likely contain baby stars of their own, can withstand this assault. The Tarantula Nebula gives cosmologists a close-up perspective of the conditions they would encounter as they further explore the cosmic noon. Observations of nearby phenomena often help researchers understand more distant ones. Similarly, Star formation in the Magellanic Clouds sheds light on similar processes in the furthest reaches of the universe. Planets in our planetary group contribute to the investigation of exoplanets. Correspondingly, research on interacting galaxies directly adds to our understanding of the turbulent origins of the universe. JWST was built to study ancient galaxies formed at the beginning of the universe directly, and researchers have been enjoying testing this capability. However, neighboring regions can often serve as analogs for older, more distant conditions. A deep-processed image of the galaxy cluster SMACS 0723 in the southern constellation Volans was one of JWST's first pictures, and the first made available to the public. This exposure, which took 125 hours compared to weeks for Hubble's various deep fields, captures galaxies in detail. These distant galaxies, even fainter and